The smallest scale one is a mission that I'm actually involved in with colleagues at Stanford called MDOT, is basically a cute little miniature starshade. Instead of being 50 meters across, it's only about 30 meters across, attached to a small satellite, and operates with a tiny little telescope and a little CubeSat that's about this big, sort of the size of a Planet Labs spacecraft. And full-size starshades need to be 50,000 kilometers away from the telescope. This miniature one only needs to be a few hundred kilometers away. And so with careful orbit design in low Earth orbit, we can get the two of them lined up for about 5 minutes every orbit, far enough apart that they can operate as a starshade and at least test the concept. The next opportunity to test the coronagraph technology comes with a mission called WFIRST. It would fill a whole talk talking about what it's for. Mostly it's a cosmology mission. It's got a huge wide field camera to take pictures of galaxies. But because it is the next major NASA mission, we have squeezed a prototype coronagraph on it. It'll only be sensitive enough to see Jupiter-like planets, but it'll give us a chance to show that all this fancy technology actually works in orbit. And Jeremy and I are both involved in the coronagraph for it. There's also a chance that a starshade could be added. One of the nice things about starshades is you can launch them later and they can catch up with the spacecraft. As Jeremy mentioned, once you have a starshade, it takes a couple of weeks to get to a new target, during which you give the telescope back to the people who want to do exciting cosmological science looking at galaxies. And then you get back to looking at planets with it. So these two missions, which could happen in the next decade, will demonstrate the technology. Astronomers are now trying to decide what to do in the decade after that to go for things that could reach the full Earth-like sensitivity. And there's two missions on the drawing board for consideration. HabEX, as Jeremy mentioned, is the Habitable Planet Explorer. It's designed from the ground up only to do exoplanets. It's a thought experiment to be what's the smallest telescope that could still have a good chance of seeing on the order of 10 Earth-like planets and measuring things like oxygen in their atmosphere. To do that, it's a 4-meter telescope with a huge, solid, incredibly stable mirror, also with a starshade, and a coronagraph. It would use its coronagraph to be nimble, to survey new stars. Then when you find one you really like, you send the starshade to it, and you spend weeks measuring the composition of the atmosphere. The other mission, we advance, there we go, slide, something called LUVOIR, the Large UV Optical, we're terrible at acronyms, Large UV Optical IR Telescope. It is almost a thought experiment in the other direction. It's what's the biggest mission that you could imagine NASA doing on 20-year timescales, with a goal of doing up to 50 Earth-like planets, as well as a huge amount of cosmology, solar system science, a million other missions. It would be an 8 to 15 meter across telescope, like a scaled-up version of the James Webb telescope. Too big to work with a starshade, but because it's so huge, it can have a really powerful coronagraph. And just to give you a sense of this, I'll show this movie that the California Academy of Sciences made for me to show the scale of LUVOIR. There's the Hubble Space Telescope pointing at Earth, which it doesn't normally do. LUVOIR actually would be nowhere near Earth, but we've brought it in for the sake of this picture. There's LUVOIR coming into the image. There's LUVOIR continuing to come into the image. There's finally the back of LUVOIR. Yeah, for copyright reasons, we're not using the music. So we have reached a point where we can realistically contemplate things this much bigger than Hubble, which would have the ability to potentially search hundreds of stars for Earth-like planets. Based on what we know from things like Bill Baruchi's Kepler mission, we could expect it to get as many as 50 Earth-sized planets that it could get the spectrum of and tell what they're really made out of. So I think we'll stop there and move into the question phase of this process.
Well, thank you. Thank you very much. So you basically say everything I wanted to ask you.
We're bad.
Now, I have a very direct question for you, Bruce, first of all. Adaptive optics has been in existence for 20 years now. We both started our career in adaptive optics, right? Mm-hmm. And my question
30,
is...
we're old now.
Let's keep the 20. 20 is better. It's a better decade. Yeah. So my question is, why did we not start building those instruments already? What's the limitation? Why is not already? We don't have already a small adaptive optic system in space.
It's a mix of, I think, politics and technology development. So although we have had these wonderful adaptive optics systems, things like Keck for a couple of decades, the level of performance you need to really see the Earth-like planet, you end up having to worry about really complicated fundamental physics, like the polarized quantum mechanical nature of light. And even demonstrating in the laboratory has taken 10 or 20 years. The other thing is NASA takes a long time to advance missions, and NASA is very unwilling to say we're going to fly a mission until you've demonstrated in the laboratory that every piece of its technology is going to work. For example, they didn't maybe demonstrate everything the James Webb Space Telescope needed before they started that project, as a result of which it's taken 20 or 30 years and $10 billion. So 10 years ago, a community of astronomers thought that the technology was not mature enough, and also that we didn't know enough about planets to justify a mission like that. And hopefully now that calculation has changed.
You, Jeremy, you agree with this? For the Starshade specifically, for instance?
I do. Well, I mean, the interesting thing about Starshade is it's actually not a very new idea. So it dates back to 1962. It was a paper written by Lyman Spitzer, who's generally considered the father of the Hubble Space Telescope. So he was very well known for getting that through and getting NASA to build the Hubble telescope. But in that same paper where he proposed a big telescope in space, he suggested that we could build a big screen and fly it out in front of it and detect planets. So it's fascinating that the whole concept of a starshade dates all the way back to Lyman Spitzer's first paper. And every 8 to 10 years or so since those early 60s, somebody's come up with a paper proposing something similar to the starshade. The problem was the technology simply wasn't there to do it. No one had yet really come up with that particular shape we showed. And the engineering behind making a starshade was just not something anybody could accomplish. There were some proposals that were somewhat similar to that in the late 60s, early 70s. But so it was a combination of just the cost of doing it, and the technology just wasn't really there. And it took some of the work done by several people, including some things in my lab, to really get to a point where we had a concept we thought we could build. And even then, you know, this was probably 2010 or so, maybe 2008, when we first said, oh, we have something we think we can do. And then it's been 10 years of work in my lab, in labs at Colorado, and different companies, and mostly JPL, to sort of sort out the mechanical engineering of how would you do this. It has to be incredibly precise in its shape. The shape of those petals really matters. You have to get it right to about the width of a human hair. It has to be deployed to the positions that exactly where you want them to be, to within 0.5 millimeter. So these are really tight requirements. Now, we've done that. We've actually built these petals, we've measured them repeatedly, and we've met all these requirements, but it took a lot of years of development.
So, but we did not send yet this kind of starshade in space. So how can you convince NASA that you are ready, that the technology is mature enough?
Well, NASA has a program right now they're calling S5, Starshade to TRL5. So NASA has this, they love acronyms, and it has this concept they call technology readiness levels, and they go from 1 through 9. So TRL1 means it's just an idea you had, and isn't this a really clever idea? And TRL9 means it's something that's actually flown in space and worked on a mission, and you know it'll happen. NASA won't start a mission until all of the technology is at TRL6, which means it's been tested on the ground in an environment very similar to what it will see in space. Well, it takes time and effort and money to get something from TRL1 to TRL6. And NASA is investing in that. So it's not that they're not interested. It's they have a process, and that's going on now. It's run out of JPL, the Jet Propulsion Laboratory. And they're very methodically marching through all the key technologies to make the Starshade work to demonstrate they're at TRL5. And then they'll get, if that happens, then the NASA will invest in what's called pre-phase A studies of a mission that'll get it to TRL6, and then they can start a real mission. So it actually is the case that NASA is very enthusiastic about it and wants to see it happen, and they're working through this process.
So Bruce, Adaptive Optics is going through the same process as well?
Yeah.
Together?
For the space version of it being tested in laboratories to show that it operates at performance levels close to what you'd need. In some ways, it's easier to test adaptive optics in a laboratory. The mirrors are like this big, They don't care whether they're in zero gravity or anything like that. They don't have, you can actually fit them in your lab as opposed to the Starshades,
Right.
where it's very challenging to come up with it. You can't actually take a 50-meter Starshade and hold it upright and shine a 50-meter beam of light on it and show that it blocks the beam of
Right.
light. So Jeremy's group has done tests of tiny little Starshades like this.
Yeah, so there are many things about the Starshade that have to be proven, and what we're doing in our lab that Bruce alludes to is you have to convince people that the optical theory you're using to predict that this works is valid over 9 orders of magnitude. And there aren't many theories that, or 10, that you can say that about. And so people wanted to be convinced. So in Bilab, as Bruce said, we built these little 1 to 2 inch Starshades, and we put them in a tube in the basement of the chemistry building that's 75 meters long. And so we have a laser at one end, this little Starshade in the middle, and a camera at the other end. And it's taken quite a few years. We wanted to get to the point where we could demonstrate we had a shadow as dark as what we're trying to predict for space. And it turns out we didn't. We got very, very close. We're pretty much there. But it turns out that physics theory we're using doesn't actually span 10 orders of magnitude. It spans about 8.5, maybe close to 9. So when you get to this little Starshade, the gaps between those petals are teeny. They're like microns. They're less than the width of a hair. And light behaves differently over these little narrow gaps than it does over big gaps. And so you suddenly had to worry about the quantum effects, nature, the electric field nature of light, which don't apply for the big one. And so we were close enough that we passed, and that milestone's been checked off. But it's been a lot of work to get there. And that's just one of several technologies, figuring out how to deploy it. There's some beautiful videos of full-scale Starshades in the high bay at JPL, watching it deploy, and a lot of really great work that's been done.
So Bruce, you are one of the few person who has been operating an adaptive optics system from the ground for a long period of time. So what did you learn of this GPI survey? What's the major scientific and technological results, you think, of this survey?
So the survey Frank is alluding to was with the ground-based telescopes to look for these giant Jupiter-like planets in the outer parts of solar systems. And the main scientific result we got was that giant Jupiter-like planets in the outer parts of solar systems are extremely rare, in contrast to Earth-like planets, where there's almost a couple of Earth-sized planets around every star, not always at Earth locations, but packed into inner parts of solar systems. You're like stumbling over Earth-sized planets all over the place. Jupiter-sized planets, or bigger than Jupiter planets out where Saturn is, maybe 10 or 20% of stars have planets like Jupiter. So a recurring theme in astronomy, exoplanet astronomy, is just how weird our solar system is. One of the many ways it's weird is that we got a Jupiter. From a technological standpoint, what we've learned that will inform the search for Earths is just a lot of how to do science, what to do with the images, to remove the leftover starlight, how to be confident when you could see in that movie I showed, there's hundreds of little blobs next to the star. Those weren't planets, they weren't little blobs coming off from the star, they were wave interference of light making a complicated pattern. And we can look at those and understand how bright they are compared to this planet, what kind of planets we could have seen, how much that noise corrupts our measurements of the planet, and so how much we should believe it when we think we see water or methane or something like that in a planet's atmosphere. So more than anything else, I think we learned how to do science, the importance of having advanced data processing software, having a clear flow so that you understand what your data means when it finally gets out the back end. And that's kind of the greatest value of doing these demo missions like MDOT or the Coronagraph on WFIRST. They'll show the technology, but like Jeremy was saying, you can show the technology in the lab to some extent, but you can't do science in Jeremy's basement of the chemistry building. If you actually want to learn the complexities of trying to get science images as these starshades line up, you have to actually do science.
So you mentioned the WFIRST mission. And it seems to be this WFIRST mission will basically put you together, working together, a Starshade and an adaptive optics system, right?
Well, there's no adaptive optics with the Starshade, but yeah. We hope. I mean, baseline right now for WFIRST is a chronograph, and the importance. I mean, really pointing out the importance of flying this chronograph in WFIRST. It will be the first instrument in space that has deformable mirrors and an adaptive optics system.
Can you tell the story of WFIRST in the short version?
Of how
Because a
it
lot of
happened?
people don't, I'm sure,
Where the
are not
telescope came
aware
from and
where
all
the
that.
telescope comes
I mean,
from, where the idea comes
so
from.
Bruce alluded to the fact that 10 years ago, there were some things proposed. So if you don't know, the astronomy community every 10 years under the auspices of the National Academy of Sciences does what's called the Decadal Survey of Astronomy and Astrophysics. So they form a steering committee of noted astronomers, leaders in the field, giants in astronomy. Bruce is on this year's panel.
Giants in astronomy plus me. Yes.
Yeah. But they form this steering committee and then a whole bunch of other panels to survey the entirety of astronomy to have the community develop what they consider the priorities in astronomy for the next decade. And this is handed from the Academy to NASA and NSF and the Department of Energy. And the agencies take it extremely seriously. This is what they do. So if you look at every great, what's been called the great observatories, every large telescope in space, Hubble, Chandra, Spitzer, and so on, these were all the top recommendations of the Decadal Survey in that decade. So the 2010 Decadal Survey recommended a version of WFIRST. Actually, it was called WFIRST in that. And Bruce was actually chair of that subcommittee. And this was going to be NASA's next large mission, which was supposed to have flown already because the decade's over. And what happened was because JWST got so delayed, there was not enough money to build the version of WFIRST that was being proposed. So then they tried a small little mini version that would be cheaper and went through that whole exercise and decided that that actually didn't do any science that was worth doing at that size. So this got tabled around the middle of the decade. And then something really interesting happened. The National Reconnaissance Office contacted NASA and said, by the way, I don't know if you know, we have these 3 2.4 meter telescopes, or mirrors, which is how big Hubble is, sitting in a clean room for a program that never got launched, that was canceled. And we're getting kind of tired of storing them. Would you like them? And so these telescopes were not designed to look out, as you might imagine. They were designed. So many people don't know that the Hubble is not the only big 2.4 meter mirror in space. It's just the one that's looking the other way. And I actually was part of a team of a very small group of people that NASA went to ask, is this worth taking? Can we do something with this? And the conclusion was we could resurrect WFIRST. Not only can we now do WFIRST, the original version of WFIRST was a 1.5 meter mirror, and these were 2.4 meter mirrors. So now we could really do it well. And the mirror is like ready to go. And so this had a great swords into plowshares aspect to it. And NASA decided to go ahead and take the mirrors. And so we're using one of them, the one that actually had a telescope built with it. There's basically one full mirror, a telescope assembly, and then a couple mirrors that hadn't gotten to the point of being put in telescopes yet. And that really jump-started WFIRST. And so we're using those mirrors. They're being repolished as we speak. That's actually almost done. And they're upgrading some of the hardware. And we're actually pretty far along on the telescope development. And the other nice thing about it being 2.4 meters instead of 1.5 meters is there was extra room. And Bruce alluded to that. Because there was extra room, we could put a chronograph in there, which was sort of what I was urging to happen, obviously. So that's sort of how CGI, how this chronograph in space happened. It was very fortuitous. And in the same sense, where we've been studying, I've been co-leading a study of what could you do flying a Starshade with WFIRST. So as Franck mentioned, one of the nice things about a Starshade is whatever telescope's up there, you can just rendezvous with it. You can just go, and because everything's happening outside the telescope. Your average, everyday, ordinary telescope will work just fine. And WFIRST is the next big telescope that's going to be in space. And so we're kind of rushing to get Starshades to the point where we think we could launch it in time to meet with WFIRST before WFIRST runs out of fuel and is all over. And so that's one of the many proposals that have been gone into the Decadal Survey that's happening right now. So it's 2020, it's the next decade. And so Bruce and I, well, Bruce on the steering committee, I'm on another panel, but we'll wrap up by the end of the year.
So what what will be able to do, what CGR will be able to do, what the coronagraph and the,
Right.
is it a GPI in space, basically?
Roughly speaking, yes. And the bad news of doing it with WFIRST is the WFIRST telescope wasn't designed for this. It's got a very complicated shape. The spacecraft isn't perfectly stable, and so you can't get to the Earth-like levels of sensitivity. Plus, you have to let the cosmology people use the telescope to study galaxies all of the time. So simulations say it could see planets like Jupiter more sensitive than GPI. GPI can only see planets like Jupiter when they're young and hot and really glowing. It should be able to see a couple of mature planets like Jupiter and measure their spectra, but it's going to take a long time for it to do that, and really the list of planets it could see is about this long. Okay. Although we know all those planets because they've been detected by other techniques. So it'll prove the technique. It'll be beautiful for studying asteroid belts in other solar systems, a topic that we're not really addressing here, and a handful of planets, but it's not going to revolutionize the field scientifically. It's really more about showing that the technology works in space.
NASA has officially designated CGI as a technology demonstration instrument. It's not, which means it's built to slightly lower standards of reliability and higher risk to keep the cost down, but it's nominally there to show we can operate a coronagraph in space. But as Bruce alluded to, the way you show an instrument works is by doing science with it. Yeah. And so that's the hope.
So you alluded my next question. You say cost. Are we talking about $1 billion? Are we talking about, what's the cost of those instruments, specifically WFIRST?
The cost of the whole WFIRST mission, according to current estimates in congressional language, is $3.2 billion, which is a number you should compare to $10 billion for James Webb, or the question of how much the Hubble Space Telescope cost is actually beyond modern accounting technology to answer. Yeah. We need sort of quantum accounting. There is not an answer to that question. People have tried to. So they're substantial, but they're not bank-breaking levels of missions. And the chronograph is a small fraction of that.
Right.
And then the Starshade.
Pretty small. Well, Starshade would be, so that's not part of the 3.2 billion. So should the decadal come forward and say that's a great idea and there's a proposal and it wins, the Starshade would be on the order of $1 billion. Oh, somewhere between 750 million and $1 billion, that neighborhood, to go up and rendezvous. But that would have to be, that would be a separate mission funded on a separate line, and Congress would have to appropriate the funds for that. And so it's a little bit early to make predictions about that.
So kind of a personal question, how did you two get involved into those projects? What has been the motivation for you? You wake up in the morning and you say, I'm going to build a Starshade in space? So you basically met someone in the hallway who told you about the story?
No. Well, I'm not an astronomer, right? So I kind of fell into this. I had worked at Stanford on a physics mission for quite a few years, and then I was actually a stay-at-home dad for a couple of years and had taken a pause. And then I got the job at Princeton and had to start a research program. And the timing was just right. At the time, NASA was looking at something they called the Terrestrial Planet Finder, TPF, which in its concept at that time, which was 1999, the little glossy book about it, was actually 5 satellites flying information as an interferometer. It was a technology we didn't talk about today for seeing planets. And it happened. I was a new assistant professor, and they were looking for faculty to get involved in this mission, and I just thought the science was really amazing. It was a combination of the science being amazing, for the same reason you're all here, the idea of imaging another Earth-like planet, and the technology was the kind of thing I had been working on, multi-satellites flying around, and so I basically went to their proposal briefing and teamed up with some industry folks, and then took us about a month to decide that it was crazy, the 5 satellite thing doing this. And we came up with a particular version of a chronograph. And I just started getting grants, building a lab, and suddenly found myself doing astronomy. And it was really kind of fun and exciting.
And you don't regret it?
No, not at all.
We're recording.
Yeah.
What about you, Bruce?
I'm more in the example of people who are basically still doing their PhD thesis again in their 50s. So my PhD thesis involved looking for objects called brown dwarfs, which are bigger than planets smaller than stars, and I built an infrared camera to look for them and failed completely to find any, and then got involved in new infrared cameras in this adaptive optics and failed completely to find any brown dwarfs, and then
You
said,
know that a lot of people have been doing that. So
Yes.
You should mention that. A lot of people
other
have been
people found
trying.
brown dwarfs, just to be clear on this. Yeah, it's not that they don't exist, it's just I was looking in the wrong place with the wrong technology for the wrong objects. And so I said, let's do something harder, like planets.
Yeah,
They're even harder
why
to
not?
see. And turns out we got sort of lucky about it. I mean, I am an astronomer, but I'm an astronomer who likes technology. And so on the edge of matching the technology we can actually build to the scientific problems that are actually interesting, I think.
All right. So we talk about WFIRST. You mentioned HabEX, LUVOIR. Do you truly believe that we will one day build something like a LUVOIR, a 16-meter telescope? Do we have the
You can take a
scientific
fifth on this if you
motivation
like.
for
Yeah.
that?
I mean, I can answer the scientific and technical question. Whether it will happen or not is a hard question. I think there is no fundamental technological issue that prevents either of these HabEX or LUVOIR scale projects from being built. Lots of things are better than they were even 10 years ago. Rockets are a zillion times cheaper. There are large rockets to launch large systems into orbit. The optical physics of the coronagraph and Starshades has been validated in the lab, and we understand it in a way we didn't 10 years ago. And we know there are planets out there based on Kepler and other missions that we could successfully image. So I know we can do it. The question is, will we? And that's both an astronomer question, and that is where I have to take the fifth, because the decadal survey committee that I'm on is supposed to make this decision. There's a lot of other exciting things to do in astronomy too, and which one to prioritize is a hard question in an era of extremely limited resources. And then it will take national levels of resources to decide to do this, and that's a conversation with Congress and the government.
So Jeremy, before you answer to my question, if you have any questions, we're going to take questions now. So you can start lining up in front of this microphone. Thank you. Go ahead.
Well, I don't really have anything to add. I mean, you know, Bruce is much more deeply involved in the process of prioritizing missions, but, you know, basically everything he said. I mean, I've worked with Congress enough now over the years to understand the fickleness and sensitivity and the challenge of raising a lot of money. But it's also the case that sometimes when you watch TV and read the paper too much, you get an image of Congress that's not the most positive one. And there really are professionals on the Hill and people who have made their career as staff who really do understand the science and understand what NASA is trying to achieve, understand the importance to the country of doing these big science programs. And so while yes, there's been a lot of talk about budget cuts, and yes, they're very frustrated with James Webb, I don't believe that the country is going to abandon large astronomy. And I get that having spoken to people on the Hill. So it's really just a matter of what's the thing that's going to capture the imagination next that they're going to fund. Do I think these will ever happen? Yes. One of these days we're going to have a big telescope in space that will image exoplanets. Is this the next thing that's going to happen? That's a really hard question to answer, and that's why we have this decadal survey process.
So, and what about the other partners, the people we've been working with, the Europeans, the Chinese, the Japanese? Are they planning missions like this, or it's really only NASA?
Well, something like LUVOIR or HabEX are going to be international efforts. So there will almost certainly, I mean, there are international partners on WFIRST, and we partner with the Europeans on missions that they do. So I don't know of any mission of this scale to image Earth-like planets. I mean, this is something that the US has really taken the lead on. The Europeans, if you go back to the 1999-2000 timeframe, the Europeans also had a mission that was 5 satellites interferometer, just a different form called Darwin. So there was a lot of talk about how do we combine TPF and Darwin, and then we went in a different direction, and the Europeans didn't want to. And these are all, and then everybody sort of abandoned it when we realized that we weren't ready, and it was very costly. So I don't know. I mean, the Europeans have talked about smaller coronagraph missions, but nothing like this scale.
All right. You want to add something on this?
Not deeply. And a thread we're not discussing is what you can do with the next generation of ground-based telescopes, and that actually is an area where the Europeans are leading compared to the US. But large space missions on this scale are historically something that Europe partners with the US, but that the US ultimately leads.
All right. Okay, you are extremely popular. There is a lot of people here to ask questions, so please go ahead. Let's make a question as short as possible. Thank you.
You showed an animation of finding planets, except the planets were all face on, like you would look at a plate, not on edge, how we detect most of them. One, how did you pick that star? Did you just get lucky? And a second question, if anything goes wrong with the starshade, is there any plan to put any sort of robot repair on it to realign things?
So for my part of the question on discovering the planets, we looked at a lot of stars to find those. So it's quite possible some of them had systems that weren't lined up in the right direction. We picked them because they were young, which makes their planets brighter, because they were nearby, relatively near to the sun. They had a couple of other clues, but we didn't really know which ones would have planets. And in fact, the Gemini Planet Imager survey Frank alluded to, we looked at about 580 stars for a total yield of 6 planets and 4 brown dwarfs.
So almost all NASA missions these days are what we call serviceable. They're being designed in a way that you could pull instruments out and put them in the same way that we did with Hubble with people. This would be robotic servicing. And so, you know, sometimes missions get to a point where they're starting to overrun cost, and that's one of the first things to go, just to save money. But there is a very strong effort at NASA and a desire that future missions be serviceable. The Starshade's an interesting animal. I think we most likely would make it servable in the sense that if we ran out of fuel, we could go put more fuel in it to extend the mission. Fixing broken pedals or things that aren't deployed right or aligned is a much harder problem. This thing is, it's a very exquisitely designed piece of machinery that has to operate just right. And you can't just sort of go in and pull one out and stick it in. Yeah, you can kick it like your car, and hopefully that'll knock things in place. But so it's unlikely in the near future. So there's a lot of, so NASA definitely has opportunities in people who think big thoughts and far in the future. And there's been, for at least the last couple decades, a lot of discussion about way stations at the Earth, Moon, L1 point. There's people who've talked about why don't we just assemble it in space, because then you can make it bigger with astronauts. That requires a whole level of infrastructure that NASA would like to get to, but they're not there yet.
Thanks.
Sure.
Yeah, so you spoke about the amount of fuel that's used. So how many stars do you think you'll observe with a starshade? Over what period of time? When does it run out of fuel? And have you thought of alternatives such as maybe even geosynchronous orbits, putting the starshade,
So
lining it up where it's closer to get to it back? Yeah. Anyway.
So a starshade does not work well in Earth orbit for a variety of reasons. Probably the biggest one is you got the separation between, you have to line the telescope and the starshade up. Right. And if you're in Earth orbit, you have a very large gravity difference between those two positions. And holding it there becomes very expensive in fuel and very difficult. They want to drift apart, even in geosynchronous, because, I mean, one of them's not going to be in geosynchronous, right? Because you got two things that have to line up. So this will be in deep space. It'll be at what's called the Earth-Sun L2 point, which is the same place that WFIRST is going, and JWST is going to that place. You also have the problem that Earthshine would bounce off the starshade into the telescope. So when you start doing all the geometry of thermal problems being that close to the Earth, Earthshine, it just doesn't work there. And so yes, the lifetime of a starshade mission is typically determined by how much fuel you can have on board. And so we generally have talked about sort of 3 to 5 year lifetimes. And that gives you could probably be visiting on the order of 50 stars. And it depends a lot on the size of the starshade, which depends on the size of the telescope. So WFIRST is 2.4 meters, so we can have a smaller starshade that's closer in. So we have more fuel, but we're actually more limited in the amount of observing time because they have to have some time for cosmology on this thing too. And then HabEX is a 4-meter mirror, so it's a bigger star. So the bigger the starshade is, the more massive it is, the further away it is. So that arc across the sky is longer, and you need more fuel. So how many you can visit really is a factor of how big the telescope is and then how big the starshade is. But it's sort of that order.
Thank you.
You?
I'm surprised I hadn't heard about the coronagraph on the James Webb Space Telescope. NIRCam has a coronagraph in it.
There's 3. There's multiple
There,
chronographs.
it's got a complicated maze of
Yeah.
I know.
coronagraphs.
I designed it.
Thank you. Congratulations.
I retired from Lockheed.
Um,
And
what it-
I'm waiting to hear how they've taken it up and made it fly.
Fingers crossed.
Yeah.
What it doesn't have is it doesn't have the internal adaptive optics. And so, as you probably know, the
Yes.
James Webb mirrors aren't perfect, and they're not going to be perfectly aligned. And so the polishing imperfections in the alignment of the mirrors will scatter enough starlight that the James Webb chronographs will be limited again to kind of Jupiter-like
Exactly.
warm infrared planets. And so it will test some of the technology, but not really that quantum leap down to it's really more analogous to the movie I showed at the start than really getting to Earth's.
Yeah, it'd be better to have a monolithic mirror to do that.
That would, among other things, that would certainly help. Although the LUVOIR design has segments too.
A lot
We'll
of
see.
progress has been made, even in just the last 5 years, in developing chronographs that work with segmented telescopes. We used to think, when I got in the field, it was a matter of faith and religion that you had to have a monolithic mirror. You could not make a chronograph work. Both on-axis wouldn't work and segmented mirror. We now have chronographs that work with on-axis telescope with segmented mirrors. So it sort of gets to some of the discussion we were having earlier, that it takes time to develop these technologies to the point where they can work.
Well,
Thank you.
I hope we'll see how well it'll work in any case.
Yep.
And,
No.
We will.
we're all hoping it'll be in space in a few years.
Fingers crossed.
Everybody is hoping this, yeah.
Yeah.
So I didn't design anything, and I'm not involved with this. So naive question, why does the star shade need to be, it sounded like tens of thousands of kilometers
Right.
away from the telescope? What factors go into that?
It's actually a really simple geometric calculation. It's actually, one of my students was asked this on his general exam. The problem is you got a telescope here and a star here that's 10 parsecs away, so that's really far. And then the planet's only 1 AU. That forms a triangle. And the star shade has to fit in that triangle. But you can size the star shade, you have to size the star shade enough to cast a shadow that covers the whole telescope. So that gives you how big the star shade is. So you just slide the star shade into that triangle, and it's 70,000 kilometers. It's just trig. It's just the sine of this distance over that distance, and it tells you where the star shade has to be. And so that was really, when we figured out that it was really that simple calculation, it was eye-opening, because you tend, when you're doing the details, you tend to get buried into this problem of diffraction and really complicated integrals and how do you make the star shade create enough of a shadow. But you can really get a sense of fundamentally how it works with just geometry, and that gives you the size scale. So, that simple calculation without any diffraction, without any petals, it gets to be like 10,000 kilometers. And in the reality, it has to be maybe 50,000 kilometers. But you're at that order of magnitude.
Okay, thank you.
So this is where we're going to enter the so-called lightning round. It's 8 o'clock, and we don't want to keep you here all night, although we could. So if you can ask your question in about 15 seconds, and if we can limit the answers to about 30 seconds so we could hear from all of our audience participants here, that'd be great.
What went into calculating the shape of that star shade, and what do you really see in the image? Will the image be something where you say, wow, look, the planet, or it will be something like a diffraction pattern that you have to calculate the real image?
Well, to answer the second part first, the whole point of the star shade is it's blocking the star and not the planets. So at this point, think of the planets are like any other star in the sky. It's just going to be a point of light. And they're just really dim stars. They're 30th magnitude objects, which we actually haven't imaged yet ever. But it would be like imaging a 30th magnitude star because they pass by the star shade and aren't affected by it. The calculation of the shape is a little bit hard, certainly harder to do in 30 seconds. But basically, what Spitzer showed in that paper and figured out is he realized we had a solid circular disk. Diffraction around the disk kills it. It doesn't work. So what we've known since the 60s is you can make this work by doing what we call apodizing, which means it's not solid everywhere. It's solid in the center, but as you go out from the center to the edge, you gradually let more light get through until you get to the edge and all the light is through. So where diffraction is a problem is edges. Light hates edges. So edges make it bend. And so you try to smooth it out. And so that was the problem. Nobody knew how to make a material that could transmit light at exactly the right amount. It's a function, a very complex function of position. That's why it didn't happen for so many years. And so what we did is figure out a way to translate that into the petals. So essentially each one of those petals is that function, just repeated over and over. So on average, as you go around, the amount of light going through at any radius is what you'd want to go through had you been able to apodize it. But then it's modulated with this periodicity due to the petals. So you just have to pick enough petals so that modulation doesn't hurt your shadow. And that's how we decide how many petals are on it.
Okay, next question.
Cool. Well, lightning round. So I think I figured out that the WFIRST starshade diameter is around 30 meters. Is that right? Okay. But the question I wanted to ask, though, that wasn't my question, was, Bruce, you had mentioned earlier that launch costs are coming down. And this is something I'm sure a lot of us are following. If we get another, say, 10-fold drop in launch costs, what kind of cool astronomy could we do then? What are you looking forward to with Starship-type launch capability?
And that makes something like, it certainly cuts the cost of something like LUVOIR down to the point where it's plausible. It doesn't make LUVOIR completely cheap because it still needs to be autonomous until you move into this sort of in-space assembly mode. So it probably doesn't reduce the cost by factors of 10. It reduced the cost by sort of 20 or 30%. Means you could think about a LUVOIR-sized mission.
I just had an observation, and I thought I'd ask. I look at that star shade, and I think, wow, that looks like a solar sail. They won't need any fuel to move it around. They'll just tack it into the solar wind, and it'll go wherever. I was just wondering, is that reasonable?
No. I mean, that is a large effect, but it would be very slow. And these missions are very dependent on time. You know, yes, you can use the solar wind for doing certain things, but for the most part, it's a disturbance, not a feature for the starshade, because you really have to have the freedom to go anywhere on the sky on short notice in that direction. And the sun's only in one particular direction in the sky at any given point in the orbit. So.
All right. So I have one final question for you. Where do you see yourself in 5, 10 years? What project is going to drive you? What's going to be the next big thing for you?
Retired.
What about you, Bruce?
Fingers crossed WFIRST will actually be flying, and we might be involved in the science operations with it. But yeah, and the HabEX and the LUVOIR missions, if they fly, are flying 15 or 20 years from now. And our role is to set those missions up now, to define them and to solve their technology challenges, and then to train the graduate students who are going to get to be the scientists who get to use them.
Yep.
So.
All right. Well, thank you very much.
So, first of all, how about a round of applause for our speakers this evening? And great questions from the audience. It's wonderful to have that participation. So thank you for doing that and for cooperating with the efficiency in that. This is my favorite part where I get to demonstrate my scientific acumen and my razor-sharp mind and my uncanny ability to identify the key takeaways of the evening. So takeaway number 1, WFIRST is actually a second-hand telescope. So you may want to change the name to W2nd. Takeaway number 2, you are in the presence, as Jeremy noted, of a giant of astronomy, which I think is actually true. So it's great to have a giant of astronomy here with us tonight. I will point out, however, that the giant of astronomy has put forward a, as yet previously unheard proposal, which was not to put a star shade in space, but instead a star thumb, which might require much less precision on the micrometer scale. So I think, Bruce, that was a good idea.
That's not my thumb. That's my colleague Carrie Cahoy's thumb at MIT. And, she took that picture.
Excellent. And lastly, I think it's fair to point out that Bruce also noted how much better off we would be from an astronomy point of view if the Earth had no atmosphere. He did, however, highlight the complications that causes for what he called the life thing. So with that, I would like to thank our speakers with our usual coveted, more expensive than the Hubble Space Telescope, speaker mugs from the SETI Talk series.
Thank you. Thank you, guys, for the retirement. Thank you.
Love it.
So thank you again for a truly enlightening, literally and figuratively enlightening talk. Wonderful technology. We're very excited about the future of exoplanet imaging and more discoveries of exoplanets. And of course, the idea that we might one day image Earth-like exoplanets is truly very exciting. We thank you all for coming. Please drive home safely. We hope we'll see some of you in San Francisco. Remember, that's that city to the north. And we hope to see you back here again in March. Thanks.